Recording in progress.
Hi students, in this lecture we are going to discuss problems based on conductors. Let us see the first one. So the question what is given? A metallic solid sphere is placed in a uniform electric field. The lines of force follow the paths shown in figure. This is given in 1996 for 2 marks. See here what is the key point. It is given metallic, right? Which is a conductor. So for a conductor inside, there is no field. So no field means no field lines inside. Okay. That's why option 1, 2, 3. These three are not possible. Okay. So only option is of fourth one. Even coming to fourth one, you should see these field lines must be normal at this point, and this also must be normal at this point, because conductor surface is an equipotential surface. At each and every point, field lines must be normal. This must be normal at this point, and this must be normal at this point. Okay. See next one. A metallic shell has a point charge Q kept inside its cavity. Which one of the following diagrams correctly represents the electric lines of force? So 2003 for 1 mark it is given. So again it is a metal, right, which is a conductor and a cavity. So we have learned that no charges, no field. But in this, charge is kept inside. Now see first of all, which options we can eliminate. Option A, not possible. Option B, not possible. And option D, also not possible. Reason is, in this conductor, okay, this is now conducting substance, right? In the conducting substance, a field will be zero. So no field lines through conductor. So here we have field lines. That's why A is not correct. B also same thing. Here having field line, here having field line through conducting substance. And same logic here also. Field lines through conducting substance. That's why A, B, D, they are not correct. And coming to here, no field lines in this conducting substance, only inside cavity and outside. And one more condition is these field lines must be normal at each and every point. Okay, so option is C. Let us move on to next problem. A large conducting plate is given a charge Q. Find the charge distribution on both the faces. Given conducting plate, it is a large. Okay, charge given is Q. So we have to find distribution of a charge on both the faces. See how we start the problem. Given a conducting plate, large plate, so charge Q is given. Charge Q is given. We have to find distribution of charge on both faces. Okay. Let us take on the left face, charge is a Q. On right face, remaining is Q minus Q. Okay. So totally equal to Q. See here, key point is, since it is a conductor, inside field must be zero. Inside field must be zero, right? So if we imagine unit positive charge inside, this charge repels now this positive charge. So force will be right side. Means if we assume this is a positive, this will repel. Now this also has to repel to make net field zero. I am repeating, this also has to repel this one. Means either both have to attract or both have to repel. Okay. So I'm taking Q is now positive. So this also positive. This is now repelling. This also repelling. That means because of this one field is, it is, we have learned that field due to large sheet of charge E equal to sigma by 2 epsilon naught, right? So because of this, sigma means if a surface area equal to A, means on one side, okay, area equal to A. Now take this relation, sigma means Q by A, sigma by 2 epsilon naught, sigma by 2 epsilon naught. This field due to this one should be balanced by field due to the remaining charge. So sigma Q minus Q by A, sigma by 2 epsilon naught. Okay. Now from this we can see these two are cancelled. Remaining is Q equal to Q minus Q. That implies Q equal to Q by 2. That means now this charge distributes uniformly on both faces. So key point is, inside the conductor, electric field must be zero, right? Let us see the next one. Let's see the question what is given. Two large conducting plates are placed parallel to each other with a separation d. One of the plates is given a charge q and the other is given a charge minus q. Find the charge distribution on all faces. Next, find the charge distribution on all faces if one of the plates is earth. Earth means grounding, right? Connecting to ground. Right. Given two large conducting plates parallel, charge as a q and minus q. Right. See how we are solving the problem. So given two large conducting plates, so two large plates which are parallel and separation is d. So here separation d is very small compared to the dimensions of the plates given large plates. Okay, right. Let us see the given data. First write down here. So one plate is given charge q. One is given q. Other one given it is minus q. So we have to find distribution of charge. See how we are starting the problem. Let us take on the right face of the left conductor, charge is a q. If this is a q, on this face charge must be minus q. See why like this? Any field line that starts from here that will end on on the surface. So number of field lines coming from this surface and ending on this one will be same. That's why this is a Q means this will be minus Q. Okay, right. If this is a Q, since total value capital Q, remaining must be Q minus Q. Okay, and coming to here, it is a minus Q plus Q. Okay, so that sum of these two equal to minus Q. Here, sum of these two equal to Q. Right. Now, here also the key point is same. Inside the conductor, field must be zero. Take a point here, or we can take point here, any point inside. Okay, and field must be zero. Now see carefully. Because of this charge, suppose it is now repelling this one, then this will attract. That means because of these two, field inside the conductor will be cancelled. So same logic here also. If you take this point, this is attracting and this is repelling. So since both have same magnitude, they will cancel. That means remaining is only due to Q minus Q and this charge. Okay. And here we are taking separation is small compared to their dimensions. Therefore, field due to this one at this point. See how much? Q minus Q. If one face area is A by A, that gives a sigma. Sigma by 2 epsilon naught. This field should be balanced by field due to this charge. So it is now minus Q plus Q by A. That gives a sigma upon 2 epsilon naught. Now these two gets cancel. Q, take this one left side, 2Q. So 2Q equal to 2Q. That means Q equal to Q. Okay. That means now charge distribution is it will be distribution of charge finally we got Q value Q. It is a Q and this is minus Q. Since total charge constant, this is 0 and this also 0. Okay. So here we generalize one point. That means instead of making this calculation every time, how to find charges on outer faces. Okay, here and here, outer faces. Take sum of these two. Here, sum of these two, how much? Q and minus Q. Total is 0. Then half of that will be outside. Okay, it is here 0. So 0, 0. On outer faces, charge will be always same. First conclusion. That means directly we can get answer without making this calculation every time. Okay. So how much charge here? Sum of the charges by 2. Half of that, right? Half of the sum of the charges on outer faces. And once we know, remaining is very easy. Okay. And on these faces, charge will be always same magnitude but opposite sign. Right? Okay. Now in this, the next question is, if one of the plates is grounded, so we got now distribution of charge. So we got distribution of charge. So given Q and this is minus Q. And we got how much? 0, 0, Q minus Q, right? Suppose now this is grounded. So symbol is taking 3 lines. Okay. Now see what happens. Its potential should become 0. Okay. You can see here between these two charges attraction is there. Therefore, there will be no charge. Sorry, there is no change on the charges on the inner face of the conductors. There is no change in charges on the inner faces of the conductors. So Q and minus Q. Coming to here, no charge. Therefore, it remains the same, means no change in the distribution. There is no change in the distribution. It remains the same. Okay. Right. Now see next problem. Let's see what is given. 3 large conducting plates are placed parallel to each other. The leftmost one is given a charge Q, middle one 2Q, and the rightmost one is given 3Q. Find the charge distribution on all faces. Okay, this time given 3. See how we are solving this one. Given 3 large plates. So given leftmost Q, middle is 2Q, and rightmost one given 3Q. So just now we have discussed one important point, that is on outer faces, charge will be equal to half of the total charge. So here what is the total charge? Q plus 2Q plus 3Q. So 3 plus 2, 5, 5 plus 1, 6. Half of that, that is 3Q. So 3Q will be on outer faces. Okay. So once we get now this charge, remaining is very simple. So for this total value 3Q, this is now constant, right? So here we got 3Q means this must be 0, right? When this is 0, this must be same value, right? But opposite sign. So 0 minus 0. Minus 0 means again 0 only. No meaning of minus 0. Right. Now coming to here, total charge is 2Q, which is a constant. This is now 0. Then this must be 2Q. Okay. Next, if this is 2Q, this must be opposite sign but same value. It must be minus 2Q. Right. Now check once. On the left one, total must be Q. This is 3Q and this is minus 2Q. So net value Q. Minus 2Q, this must be opposite. So 2Q. Total is out 2Q. This is 0. Right. Total value 3Q. 0. This is 3Q. Okay. So like this, directly by seeing the problem, we can get the answer. So first getting charge on outermost, which is equal to half of the total charge. I hope you got the clarity. Let us move on to next one. See what is the question given. 2 large conducting plates are placed parallel to each other with a separation d. Given 2 large conducting plates, separation d. One of the plates is given charge Q, Other is given 3q. This is same as a previous question which we have discussed. Okay, find the charge distribution on all faces if one of the plates is earthed. The only change is now here, one of the plates is earthed, right? Find the number of electrons flowing from ground to the conductor. So given q and 3q, one of them earthed. Now we have to find number of electrons flowing. Right, see how to solve this one. Given two large plates, right, q and 3q, right? See what happens now. Distribution of charge. It is now total value 4q, total value 4q. So half of that, that is 2q on outer faces. Okay, I'm repeating. Total value 4q, half of that is 2q. So on outer faces 2q, 2q. Now each charge, this is now constant. So this must be minus q. Here 3q, this is 2q. Or you can say this is minus q. This must be exactly same value but plus. Okay. This is now distribution of charge before grounding. Now one of the plates is grounded. Okay. So this is symbol for grounding. Now see what happens. You can see these two charges are now bounded because there is no attraction between these two charges. Therefore, no change on inner faces. No change on inner faces. Coming to outside, this is now free charge. Means it is free to move if path is available. I am repeating. This charge is free to move if charge is available. Okay. That means now after grounding, see what happens. So this is now distribution of charge before grounding. Okay. Do one thing. Let us draw a diagram separately for grounding. This is before grounding. So after grounding, see what happens. Once this is grounded, charge on outer face becomes zero. Okay. How much here available? It is 2q. Now it becomes zero. When this becomes zero, this also must become zero. Students, see carefully here, while both must be same. When we are taking a point inside the conductor, maybe here or maybe here, net field must be zero. And we have learned that on inner faces, values will be same, signs opposite. One is a plus and one is minus. Because of those two charges, net field inside the conductor is always zero. So remaining is only outer charges. Then both must have same sign and same value. Then only inside the conductor field becomes zero. That's why when this becomes zero, this must be zero. Now coming to the left conductor, left one, total charge is a constant. So it must be Q. Okay. But remember for right conductor, For this one, total charge is not constant because it is grounded. There is a connection to ground. Okay. So total charge is not constant. This is a Q means this will become minus Q. Okay. This will become minus Q. That means what is our total charge on the right conductor? Initially it was 3Q. Now it is only minus Q. So how much charge has flown? That is 2Q charge that has flown from body to ground. Okay. Suppose Q is a positive, then this is a positive. What it means? Its meaning is that electrons are flowing from ground to body. Ground to body. How many electrons are flowing? That we can write number of electrons into charge of each electron is equal to 2Q. Okay. Then number of electrons are flowing equal to 2Q by charge of electron. And students, don't take here negative value, okay, for charge. This is only modulus of charge of electron. Means 1.6 10 power minus 19. Then we get number of electrons flowing from ground to body. Okay. Because we have taken Q is now positive. Okay. Now it is only minus Q. That means electrons have flown from ground to body. Otherwise, 2Q charge has flown from body to ground. Right? So like this, we can solve problems. So whenever you are grounding a body, on outer face, charge becomes zero. That is a key point. Okay.